Hello everyone, my name is Katerina Galitskaya and this is the third tutorial in my 6 episode series on antenna simulation in Nullspace. In the previous episode, we created an antenna array based on a single bow tie antenna element from the first tutorial. And today we will move to beamforming, which is very exciting for me. I like this topic very much. So we will build on the previous model, but we'll make several adjustments. It will be less distance between elements, so decreased element spacing just to minimize grating lobes and to achieve better radiation patterns while steering. And we will look deeper into beamforming post-processing, see how to apply amplitude and phase weights, how to visualize the steered beams, and see how the array performance changes with the different configurations. So let's get started. Let's start with changing our antenna array. So we will do some changes to the distance between elements. If you remember in the previous tutorial, we had 4 antenna elements and the distance between elements were around lambda. I chose this distance because I wanted to maximize gain. So the more aperture we have, the more gain we have. But there are as well some trade-offs. So we maybe have some grating lobes. We can have some problems with the beam steering in this case. So for now for this beam steering, beamforming tutorial, I'm going to decrease the distance between elements, and I'm thinking to go with around half lambda. So as you see, this is our original antenna array, and we have here distance between elements is around like 300. So what I'm going to do is I'm going to do it directly from the journal. So I am just changing the here the distance to 170, approximately half lambda, and then I also unite the ground plane as one like surface to have only one surface. So that is that are the changes that I do, and I just press run from the journal, and it changes my antenna array and creates the mesh automatically, and everything is very smooth and nice. So I really like this functionality to kind of to work with the journal instead of pressing all the buttons in the user interface. So now we have antenna array with a new updated distance between elements, so around 170 millimeters, and we can move towards the our processing, right? So we go to Python, and with the simulation setup, it's very similar to what we have before. The only difference is that here I use the new updated model with the decreased element distance, and as well I use decreased step for my far field. I used to use 2 degrees, now I have one, just to have like better control over beam steering. That's the only change that I have in my simulation setup. The biggest changes that is happening is in the post processing. So with the post processing, now you can see that I can scroll and scroll and scroll this script because it gets more and more complicated. If you remember in the first tutorial, it was very short because we only had one antenna array or one antenna element. But now we have antenna array, we have beamforming, and we need to like script a lot of things. So that's also kind of gets more and more challenging and also interesting, of course. So what I have here is my function that basically finds the maximum gain at the scanning angle. So I feed it my scanning angles, and then it returns weights for normalized weights on that like maximum scanning angle, copolarization and cross polarization. And we touched on weights a bit in the previous tutorial, but we talked only about equal weights and like no phase shift. So in this tutorial we will now look into phase shift first. So if you can see here, I have my phase scans. So I now have 10 degrees phase scan and in phase scan, and then I have equal amplitudes. We will see how we will change them as well after that. So first we go with the frequency phase shift and equal amplitudes. And then as well, one difference is that I want to now see all the active antenna, active S parameters for each port instead of combined. I think because we have more coupling between elements, so like they're close to each other, it's very interesting to see how they perform, and also with the scanning. And one more thing that I have here is, well, here is that I print my maximum gain and beam tilt. That's kind of easy. And then I have some piece of code that finds upper side lobe. So side lobe suppression is very important things in antenna arrays, and also in my work, I work with the base station antenna arrays, and upper side lobe is very important. So because we don't have anything like in that direction over our main beam. So I want to find my upper side lobe in the radiation pattern, and I also want to see how much side lobe suppression I have. The rest of the code is plotting, so it's very similar to, like, it's almost identical to what we had before. So now we can look at what we have with the equal amplitude and 10-degree phase shift. Here we have active S parameters. So as you can see, they are not equal for each four ports. It's because we have now very close elements to each other and they couple, and also we have like different elements on the, we have maybe edge effect on edges. Some elements in the middle, they have like two elements around them, so they are different. So that's why it's very important to control these active S parameters. Then we have our gain, and if you remember in the previous tutorials, we had around like 15, close to 15 dB gain. Now we have a 12.6 because the distance between element is decreased, so is gain. And if you look at the radiation pattern, so we have tilt at 10 degrees, but the beam width is also much wider because, again, of the decrease element distance. And we also have our side lobe level, let's see, 13 dB approximately, right? 13 dB, which is not so good. We usually aim for like worst case scenarios 15. So let's see how we can fix that, if there anything that we can do. Let's also look at the 3D radiation pattern. So here is the 3D radiation pattern that we have. Okay, so the next thing that we want to do is to have the same amplitude, no, the same phases, but change amplitude to not equal distribution, but to have less amplitude on the edge elements and more amplitude on the middle elements. And we will see how it affects the radiation pattern. So here, what is the change? So first of all, we can see that the gain is smaller. So in the previous design, or the previous results, we have 12.6, now we have 12.25. So that's one sacrifice that we made. But what we want is look at the side lobe suppression now. So side lobe suppression is 20, which is very good. And so if we want, so it's again like the question of what you want from the design. If you want side lobe suppression but can sacrifice a bit gain, then you can go with this kind of like some harsh amplitude tapering. And the one thing that's changed a bit as well is beam width is also wider because the gain is smaller. So that's kind of the focusing of the beam is less now. But the tilde is still 10 dB. So in the beamforming, in this case, like beam steering is still the same. We just kind of want to control our pattern. We want to control beam width. We want to control gain, and we want to control side lobes. So let's look at the 3D radiation pattern. So it looks very similar to what we had before, but the side lobe level is less. So that's a good thing, at least for me. Like if in my work, yeah, gain in some projects is a very important, but in some project we can maybe sacrifice a bit of gain but have good side lobe suppression. So that was all about beamforming. Well, of course, we can talk more about beamforming. It's like very big topic, but the main functionality, kind of post processing, how to approach this topic is there. And next time we will look into radom integration. Also, very important topic: how to import some like external 3D models, how to work with them, how to assign mesh, and then radom effect as well. So how does radom affect the antenna performance? That's also very interesting things. Thank you very much for your attention. Bye bye.